It is the second part of section 5.3, the method of Lagrange multipliers. To understand the method, let's begin with a very simple example. We try to maximize or minimize a function defined on two-dimensional space and subject to a constraint, equality constraint. Now, if we consider a typical example like this one, and that is, there is a maximum for f of x. Now, g of x equals c is curve, as in this red curve. Now, if we are considering level curve for f of x, then we can make such kind of a level curve along with the constraint. Now, we'll try to use our knowledge around the derivatives. Derivatives are always positive direction, and gradient is the direction of fastest increasing direction. Now, for this level curve means that f has the same value along this curve, so that in normal direction, the value will change fastest. So the gradient of this function is normal direction of the level curve. And also the same, this is a sort of level curve, so that now the gradient will be the normal direction. Once the maximum is happening at a point, of course the point x should satisfy this equation. Then at the point, and if we measure the gradient, then the gradient of f and gradient of g must be parallel. It can be, they can be opposite directions. However, they are parallel, along with some multiple number, variable. They can be expressed in this way. Here, gradient of f is same as with the coefficient gradient of g. That means that the gradient of f is parallel to gradient of g. In this case, lambda is called the Lagrange multiplier. And here, g of x equals c. Now, we start with a two-dimensional problem. In this case, here, there are three variables to decide. And x has two components and lambda. So there are three variables. Now we have three equations. This gradient will make two equations, and here the constraint equation. So eventually, this system has three variables and three equations. So we can solve it having finite number of solutions. If it is a linear system, then it can be a unique solution. But usually, because it's a nonlinear problem, it may have more than one. And in fact, because of the number of equations is the same as the number of variable, it has a finite number of solutions. Okay, so that's the system we have to solve to find here the optimum value. Okay, of course at x, this should be satisfied. So this constraint is more important to satisfy. Okay, yeah, let's see this example. And we want to use the method of Lagrange multipliers to find the extreme values of f of xy equal x squared plus 2y squared on the circle of radius 1. So this is constraint. So here, this portion is now g of x. Now, that portion is f of x. Okay, so gradient of f is lambda gradient of g is now, that is 2x, and now 4y, and gradient of gx is same as 2x and 2y. So we have this equation. So that one makes two equations here, and this last one is coming from the constraint here. So we have three equations. From the first one, now 2x equal 2x lambda, so that it can be written in this way. So here that is 2x and lambda minus 1 equals 0. That equation 1 can be written this one, so that here x can be 0 or lambda equal 1. Okay, we have here now, once x equals 0, okay, so once x equals 0, then from third equation, y must be here plus minus 1. And secondly, if lambda is 1, then lambda is 1, then from second equation here, y must be 0. That means that from third equation, x must be plus minus 1. So eventually, the points we have to consider are here, the points on the circle. You have to find the points on the constraint. So that, but here is indicating that once x equals 0, then y is plus minus 1. So this one and that one. Once y equals 0, then x is plus minus 1. So that point. So for each point, now you can evaluate the value here. So for this point, f is 2. For that point, now there is 1, 0. So that if you plug here x is 1, y equals 0, then f is now 1. And this point, again, f is 2. And that point, f is here now 1. So maximum is 2, minimum is 1. Okay? So in this way, you can use Lagrange multiplier technique. Now, here, we'll try to use the technique for solving the optimization problem with the inequality constraint like that. So we try to minimize x squared subject to x is larger than or equal to 1. In this figure, now x is larger than or equal to 1. That means that only this side is considered. Now for y equal x squared, we try to minimize, then apparently the minimum value here, x equal, the function value, must be here now 1 at x equal 1, right? We know the solution. Now, by using Lagrange multiplier technique, we'll try to see if we can get the same solution. Okay. Now, for the constraint, we may write in this way, x minus 1 is larger than or equal to 0. And here, we defined for this original f of x, and along with the constraint, we make a linear combination. X squared minus alpha x minus 1. That is called Lagrangian. And now alpha is Lagrange multiplier. And earlier in this example, we tried to use lambda for gradient. But before differentiation, here, you may write down this one as f equal lambda g, or more generally, you may write down this one, for example, f plus lambda g, defining minus lambda becoming lambda. So start from this one, you may change in this way, And then now if you make a derivative, then you can reach that one. So even in this equation, you may think of lambda as the Lagrange multiplier. Okay. So exactly the same here, we combine them. And however, this is inequality. But now alpha is the Lagrange multiplier. Okay. Here, this is original problem. And now after introducing Lagrangian, we try to change the f of x with here that maximum alpha, the Lagrangian. Now subject to the Lagrange multiplier larger than or equal to 0, because it has inequality, we may have to choose alpha either positive or negative. Right now, in front of alpha, there is a negative. Now, later on, we'll see here, we have to choose negative. And you have to choose the sign, positive or negative, appropriately. But here, in this case, the choice is negative. We'll see the reason we are choosing negative here. Okay, so this is original problem. Now, that is here minimum, maximum, so that min-max problem with Lagrangian, and subject to now alpha is non-negative. Here the claim is that the original minimization problem in 5.27 is equivalent to the min-max problem in 5.29. This problem, that problem are equivalent. Okay, let's see the proof. Okay, now there are 3 cases for x value. X is larger than 1. Then once we consider over there that portion, maximum with alpha non-negative, so that then if we consider that portion only, then here minus alpha x minus 1, x is larger than 1, so that that will be here positive, and is non-negative along with negation. This value is negative, so that maximum happens when alpha is 0, right? So the maximum value, the optimal value alpha star must be 0, so that eventually here now this Lagrangian becomes the original objective. How about x equal 1? Then now that portion 1, that is 0, then alpha can be arbitrary, so that here alpha can be arbitrary. Now once x equal 1, and then alpha can be arbitrary. However, this is 0, so that the Lagrangian becomes the original objective. How about the last case? X is now smaller than 1. Then this portion is smaller than 1. So this portion is negative. Along with that, and this positive and this non-negative, so that the maximum value will be infinity by choosing alpha larger and larger. So the value is infinity. However, now here in front of the that portion, and we have a minimum with respect to x, so that if it grows, then min-max part will be against that, so that here in this portion will try to change it when x is less than 1, then this inside the maximum blows up, so that this min part will push the x to become larger than or equal to 1. So that try to increase the value so that it is over 1. So it means that mean with respect to x forces max alpha to behave so that eventually this min max problem is equivalent to the original problem. That means that it will produce the same result. Okay. Now, so we may consider this problem as primal problem. That is primal, and again, because it's equivalent, we may say this is primal. Okay. Now here, we'll define dual problem of the primal. Okay. Here, that is now primal problem and equivalent to the original problem. Now, dual problem is simply we are changing here mean and max so that it becomes now max and mean. Of course, minimization is about x, and now maximum is over alpha. So that is now dual problem of the primal problem. And here, when we try to solve the problem, we first try to solve this portion. And then, now after solving this portion, and we try to change everything, and after solving this, we'll see the detail. And this Lagrangian will be changed into a function of alpha. Then, now, along with the maximization, we decide alpha, and by seeing the alpha, we decide x. That's how we are solving the problem. And let's see here how to solve it. Now, we start with the maximum over x for the Lagrangian. And now, here we use the calculus technique and differentiate it and equate to 0. So for that Lagrangian, if we differentiate with respect to x, and that is 2x, and that is now minus alpha equals 0, that means that x is alpha over 2. And here x is replaced by alpha over 2. Then we reach at here this term, that is a function of alpha. So Lagrangian is now expressed as a function of alpha, and there's no x variable involved. And now we can maximize this portion, this function. And here, so we have to maximize it. Now, to maximize it, again, you can use derivative technique so that once the maximum is now, the maximizer is larger than equal to 0, then that'll be the solution. But that one, from this one, if you are making derivative, then that is 1 minus here alpha over 2. If it is 0, then we can say alpha equal 2. So that we get the maximizer alpha star is now 2. And if we are using alpha star is 2, then from that one here, the x becomes now alpha star, which is 2 over 2, so that must be 1. Okay? So here you can get 1, or using the Lagrangian objective, once we choose alpha, then by using Lagrangian objective, you can see that, we put here now alpha is 2, then x squared minus 2, x minus 1, that is exactly this one, and we can rewrite in this way, and then now the Lagrangian can be expressed in this way, and this is quadratic with a vertex and 1 and 1. when x is 1, the value is 1. That is exactly here. You can see that from the figure. When x is 1, the function value is 1, right? Okay. In this way, we can use the method of Lagrange multipliers, and the technique we explored in the second part of this lecture will be used to solve the object function of the supported vector machine. Okay? Okay, we'll continue in the third part. Thank you.